Welcome to the presentation of the work Shape My Face, Registering 3D Face Scans by Surface-to-Surface Translation. My name is Mehdi and I'll be presenting today. This talk is based on the paper of the same name, which is currently in review with IJCV and available on arXiv. Geometric deep learning has had a lot of success with 3D, thanks to the development of convolutions for point clouds and meshes, but several challenges remain. One of them is that the choice of discretization of a surface is not unique, as we can see here with this bunny or with the face. The other is that real data is noisy. This is typically tackled by preprocessing, often done manually, which can include steps like registration, subdivision, meshing, and cropping. Registration is the task of finding a common representation for surfaces. It's often done with optimization-based methods, which solve a new instance of an optimization problem every time, often a non-convex, difficult optimization problem. Recently, we have seen the development of learning-based methods for surface registration. Learning-based methods are appealing because they promise to offload most of the work to training the model, and to reduce the registration of a new surface to a single inference pass. This would be much more efficient than solving a new instance of a non-convex optimization problem, especially, for instance, on a phone or some other embedded device like a scanner. The issue with these methods is that so far they have focused mostly on rigid registration, which means translation, rotation, and possibly scaling. When we want to register face scans, we need non-rigid registration to deform a template into a raw scan. One method has been developed to perform the non-rigid registration of raw face scans in a learnable way, and we will present it as the baseline in this talk. The baseline is an autoencoder architecture that takes a processed input and applies a PointNet encoder to produce different embeddings for identity and expression, from which are decoded blend shapes with MLP decoders. The issue with this method is that it requires careful processing of the data, doesn't really offer great generalization, and produces noisy reconstructions, as we can see here, even on a training set. We propose SMF, a pipeline for unifying registration, morphable model, and generation in a single model. We want to minimize the need for manual preprocessing, and to provide a compact model that generalizes well and is robust to noise, for example for use in embedded scanners. We dynamically sample a point cloud from the input. This makes the model discretization agnostic since we can sample from many different modalities. We use a modified PointNet encoder optimized for small batches so that we can sample high-resolution point clouds from the input. We also introduce a novel visual attention mechanism to replace cropping with learned segmentation and gating and for improved robustness to noise. The impact of the attention mechanism can be seen here with this experiment where we add ambient noise to a scan. The models trained without attention are much less robust to noise than the models trained with attention. This is further seen here with these renderings where we can see that the attention mechanism successfully segments out the face and allows for usable reconstructions compared to the models without attention. For the output, we model the identity and expression components in the scan as deformation fields over a mean face. This is a blend shape model. We use mesh convolutional decoders with a novel kind of skip connections reminiscent of the inception architecture of images, which we call mesh inception. Contrary to previous skip connections proposed for GNNs, this kind of skip connection is beneficial for models that already have a kind of skip connection included in the form of a separate weight for the center vertex, for example SpiroNet++, which we use in the paper. Finally, we add a strong subspace regularization on the mouth region. This is because the mouth region in raw scans is typically contaminated by points from the teeth and the tongue. And this causes artifacts in the output where some points from the lips are pulled towards the inside of the mouth. The typical approach, which is also the one used in the baseline, is to use Laplacian regularization on the mouth region. And as we can see here, this doesn't completely remove the artifacts. What we do is that we take the mouth region in the blend shapes produced by the mesh convolution decoders and project them on specialized PCA bases. We then blend back the output of the PCA models with the blend shapes produced by the mesh convolutions using a blending function of the geodetic distance from the inside of the mouth. And this enables seamless blending. We can summarize the differences between SMF and the baseline in this table. Contrary to the baseline, we only rely on rigid alignment of the scans with the template. Our encoder allows us to sample much higher resolution point clouds from the input. We use hyperspherical embeddings for the latent space, for improved clusterability, and for their success in face recognition. Our mesh convolutional decoders allow us to drastically reduce the number of trainable parameters as well as the model size. Finally, we significantly improve robustness to noise thanks to the visual attention mechanism and to our hybrid approach to mouth modeling. Our paper includes a detailed ablation study of the different factors at play, for example, the choice of decoder, where we evaluated SMF and compared with a fully connected decoder or a single decoder, as well as different embedding sizes. We also show the effectiveness of the mouth model, as well as compare it to using Laplacian regularization. And here Laplacian regularization achieves the lowest error, but we suppose this is because it makes the optimization problem simpler and allows the vertices from the lips to get closer to the inside of the mouth, which reduces the overall error as well. We experimentally evaluate the registration ability of SMF on the same data as the baseline, which is made of 7 public ROI datasets. We also train a variant called SMF Plus by adding 2 large-scale internal datasets. Our test set is either BU3DFE when training on the 6 remaining datasets, or an internal large-scale dataset called 3DMD. We can see that SMF produces consistently low registration error, both in sample and out of sample, and markedly outperforms the baseline. In particular, on BU3DFE, SMF trained out of sample outperforms the baseline trained in sample. We can visualize some registration examples on the training set and on the test set with the raw scans, the output from the baseline, the segmentation mask produced by the attention mechanism, and the output of SMF. We can see that there is no significant degradation in registration quality for SMF between the training set and the test set, and that the attention mechanism successfully segments out the face. We can also visualize some synthetic samples obtained by sampling from the latent space. Here we have the output and the closest match in the registration of the training set. Here we can see that we obtain a good diversity of identity and expression as well as ethnicity with no mode collapse. Finally, the main outcome of the project is to do registration and morphable model applications in the wild. To test this, we have different scans from different subjects captured with different devices and in different conditions. 6 are for myself. We have 2 scans captured with body scanners. These are meshes that we cropped. 4 scans are expressive scans captured with my phone as point clouds in high resolution. We have 1 expressive scan captured with my phone at the low resolution, again as a point cloud, and 1 neutral scan captured with a professional face scanner. We can see that SMF offers consistent representation of the identity and expression of the subjects, and that the attention mechanism is successful at identifying the face. So now that we have registered the scans with SMF and obtained the latent representations for identity and expression, we can perform identity and expression transfer across subjects in the wild and across modalities. So here we have one of my expressive scans captured with my phone, and we interpolate the identity and expression components smoothly to the ones of subject C in their neutral expression, which was the scan captured as a mesh with the professional equipment. Then we can fix the identity vector for C and transfer my expression, my surprised expression vector by smoothly interpolating, and we obtain a synthetic scan of C in a surprise expression. So thank you for listening, and I hope to see you soon for the questions.